Hey everyone, and welcome to Dr. Abu RTN Academy channel. In this video, we are going to discuss part 3 of the distribution of random variables as part of the biostatistics subject. Our focus in this video will be on the discrete distribution types, and we have two types. One, binomial. Okay, binomial means two. Okay, like I have in the coin. If I toss the coin, I have the head and tail, so it is two. Okay, if I say you agree or disagree, the answer will be either agree or disagree. Have you okay or no? Answer will be yes or no. Only two options, okay? The second type is the Poisson, okay? And we'll come to all of them in detail. So in this video, we'll focus on the binomial probability distribution. And for binomial probability distribution, Jacob Bernoulli, he has set one trial called Bernoulli trial, which we're going to explain here. So the word binomial probability means that we have two outcomes only. There are two outcomes, exclusive outcomes of the experiment for event A or not A. So A means it will happen, B it will not happen, and both of them will be complementary. So if one of them, the probability of A is 0.2, the probability of not A it will be 0.8, the probability of A it will be 0.3, probability of not A it will be 0.7, and so on. So a single act of finding out whether the outcome is A or not A, okay, it's called Bernoulli trial. So Bernoulli trial only called binomial. You have only two choices, either happened or not happened, event or not event, A or not A. Many variables in the medicine have exactly two outcomes, such as survivor, whether the people will survive or not survive. The test result being positive or negative, only two choices, okay? Survivor. Okay. The presence or non-presence of genetic trait, okay? Presence or non-presence, okay? Presence or absence of disease. So here in this slide, we are defining the case of binomial distribution. So we have here 4 rules which we have to know about the binomial distribution. That each observation falls under one of two categories, okay? So either if you toss a coin, for example, you toss one coin, it will be head or tail, only one of the two choices, okay? He has a disease or disease is not there. Presence or absence of the disease, okay? Survive or not survive. So each observation will fall only under one of two categories, okay? This is the first rule. The second rule, that the n observation are all independent. For example, if I toss the coin, the probability of having it ahead is 50%. If I repeat the experiment and I toss the coin again, the probability of the head, again, it remains 50% or 0.5. So this means that the result of the observation of the second toss, it is not depending on the previous one. The third one also, it will not depend on the previous two. It could happen 5 times. So always the probability of the head, it will be 0.5. The probability of the tail, it will be 0.5 every time. Even if the first one became tail, the second one also could become tail, third one could become tail, or the first one happened as head, second and third and the fourth could happen as head as well. So the observation are all independent. No one of them depend on the previous one. So their probability remains the same. The tail probability remains the same every time, and the head probability remains the same every time. Okay, and the same in the case of the patient also. The probability of a given outcome is constant over all traits. So this is what we just mentioned. The probability of the tail, it always will remain 0.5. Probability of the head will always remain 0.5. Okay, so it will not change. The probability of a given outcome over all trails, it will remain constant, it will remain the same, okay? The probability of survive, theoretically, it will be 0.5. Probability of not survive, it is 0.5. It remains the same, okay? So here they are independent. So if the first one became a tail, there is no harm the second one, third one, everyone will come a tail, or all of them will come ahead. So they are independent, and here they are the probability 0.5 or 0.7 or 0.6 remains the same. The number of the trials are fixed. So before setting the experiment, we have to identify. For example, I want to have a test on the number of patients who had a cancer and they will survive for 5 years. So before I start the test, I have to fix a number. I say I do this experiment on 50 people, okay, who already have a cancer for the past 5 years, and see whether they will survive or no, or he just got a cancer and whether they will survive for the next 5 years or no. So before I start the experiment, I have to fix the number of the sample, the number of the individuals in my sample, okay? So the number of trials should be fixed. I have to fix it, identify and fix it through my experiment. I should not change it again during my experiment. So here, this is just what I have summarized. Each observation fall into just one of the two categories, okay? So they are mutually exclusive outcomes, either successful or not successful. So if I assume that the probability that the student will success equals P, so the probability he will not success or he will fail, it will be 1 minus P, okay? Where I can call it Q. Okay, so I can have P and Q. So Q in this case will be complementary of P, complementary, okay? So if P is 0.2, so Q will be 0.8, complementary. Both together will complete 1, okay? Will add up to 1. If the P is 0.3, so Q will be 0.7, and so on. So Q equals 1 minus P. This is the probability, successful, for example, and the other one failure, okay? Success and failure, both together should be complementary. If one of them be, the other one will be 1 minus P. The second point, that the any observation, all are independent. They don't depend on each other, okay? Suppose that you have a test, okay, of prostate cancer. And a large group of people, large cohort of elderly patient of old age. The outcome of the first patient, if he has a cancer, it doesn't alter the outcome of the second patient or third patient, because all of them are independent. Okay, each patient don't depend on the other one. The third one here, the probability of the outcome is constant over all trials. This is called homogeneity assumption. Homogeneity assumption means that I assume that the probability is constant always. For the head, it's 0.5. For the tail, it's 0.5. Okay, it's called the homogeneity assumption. For example, if you toss a coin, the probability of getting a tail is 0.5. And if you toss it again, the probability of getting the tail again, it is 0.5. If you toss it third time, it will remain 0.5. Okay, the fourth one here, that the number of trials N is fixed. We have to specify this in advance. Okay, you must specify in advance how many Bernoulli trials you will perform. For example, prior selecting the patient for a cancer registry and recording if they have survived 5 years or not, we must decide on how many patients will be included in our sample, how many individuals in the sample in advance, okay, in order to make sure it is random sample and you have set the basis. So because the basis of the experiment should not be altered later on. These are the 4 rules which has been set by Bernoulli in his trial, okay? So coming here to the binomial distribution and their equations and functions. So in this example, we are talking about experiment. If the experiment is carried out n times, I repeat, experiment n time, what is the probability that the outcome of the experiment, for example, the survival of the cancer patient, they survive or no? Okay, this is called observation. So the observation that, or the outcome that he will survive, this is called success. If I set success factor that he will survive, so this will be my success factor. So what is the probability that the outcome is success? So he will survive, okay? Exactly k times, 10 times, okay? If I repeat it 10 times, what is the probability that he will survive 10 times? If I repeat it 30 times, what is the probability that he will survive 17 times or 13 times? The k times, okay? So what is the probability that the outcome of a success, that this observation will happen exactly k time. The probability distribution of the count x of successes called binomial distribution. This is called binomial distribution, okay? With parameters n is the number of times of repeating it, and p the probability of success, the probability of survive in the case of the survive. If I'm talking about the tail and the head, if the tail is the success, so the probability of the tail, okay? So the probability here of x, when I need x to happen k times, and I want him to survive, or I want him to success 5 times, 7 times, 8 times, okay? So the probability of x equal k. X equal k means I want him to survive, probability of surviving 7 times, or probability of success 7 times, probability of success 9 times. If you recall, I told you that the success factor, the success probability is p. For example, it is 0.2. So the q, which is the complementary, will be minus 1 minus 0.2 equals 0.8. So this is q is the complementary of the p, okay? So if p is the success factor, so q will be the complementary of it, the failure factor, or failure probability, okay? So the probability of x success or happening k times equal combination of n is the total number, and k, okay? P of power k, the probability of happening of the variable k, okay? And the q was the complementary n minus k, the first one minus second one, n minus k. So this, I think it is easy to memorize. Let us write it again. So probability of x equals k, okay, equals combination of n, k, p of the selected or the success criteria of k, q, n minus k, first one minus second one, minus k. As you remember, the combination was, if we say combination nk, how to write it down? So it's called first one in denominator n factorial divided n minus k factorial, okay, multiply the last one, which is the selected criteria, k factorial, okay? So it is n factorial, n minus k factorial, k factorial. The same thing here. So he just expanded. So combination nk, it will be n factorial, n minus k factorial times k factorial, okay? Times p of power k, q, which is a complementary, n minus k. So it's better to write it in the first time if it's not given in the exam. So better to write it in such a way that combination of nk, p of the second one, power of the second one, and the q, the power of n minus k, and then you can write the combination because it is known to you. So coming to the abbreviation here, n is the number of trials, okay? How many number I'm trying. K is the number of success, the count of success. How many times I want it to be success, okay, to happen. So maybe I have 15, but I want to success to happen 7 times or 9 times or 13 times, okay? So n, the number of trials, k, the count of the success, okay? And this count of success, because it is number of experiment, it success 2 times, 3 times, 5 times. It cannot be decimal. It has to be integer value, 1, 2, 3, 4, and so on. P is the probability of the success. So P, probability of the success. Q is the probability of the non-success. So okay, if he survive, here he will die. He will not survive. Okay. So here I have got 2 new formulas. One for the mean or the average or the expected value. In the case of the binomial distribution, the success, the expected value here will have a different formula. So here mu, the mean or expected value, will be equaling NP, okay? Not XP like before, it will be NP. N, the number of trials, times the probability, okay? The variance, which is sigma square of the distribution, will be equal N PQ, okay? So NP, and just we'll add Q. So mu times Q, okay? So here NP and here NPQ. So coming to this example, the probability of a male birth is 0.151. So it is not 50% or 0.5, it is 0.51. What is the probability that exactly 3 out of 5 births are male, okay? So what is the probability of the male? Success factor, because he want them to be male. What is the probability that exactly 3 of the 5 will be male? So his success criteria here is male. So the probability of the male is the success criteria. Probability of the male is 0.51. Probability of the female will be the complementary, 1 minus. So Q will be 1 minus 0.51, which will be 0.49. Since trials are independent, okay? They don't depend on each other. The joint probability of any one sequence of 5 pairs resulting in a total of 3 males out of 5, okay, of the product, it will be, so here the first chance could have this one, male, and these two are 2 males, or any arrangement, because it doesn't matter for me who's coming first. They are independent. Okay? So this is one of the orders, the possible orders, okay? We could have the male, the first one, the male, the second one, and male third one, and the 2 males are the last 2. So first, second, and third are males, and the last 2 are female. We have different arrangements, okay? We could have the first and second male, the third female, and the fourth male, and so on. So we have a lot of probability. So the probability here, because the male has 3 chances, okay, different arrangement. So the probability will be 0.51, the probability of the first one, the male, of power 3, times the probability of the complementary, which is 0.449, n minus q. How many times I repeated? I repeated 5 times, or I have how many? The total number 5 pairs, okay? So 5 minus 3 equals 2, okay? So it will be 0.51 of power 3 times 0.49, which is this part. If you look at the formula here, you can see this formula has 2 parts actually. The first part, which is this one, combination. So I have to choose 3 out of 5. And the second part is this section, okay? In this example, actually, it is a way of proving how they arrive to this formula. So the formula has 2 parts. So here, the percentage or the probability. What is the probability? So here, the probability of getting 3 out of 5 equals the probability of the required or the success criteria, okay, which is 0.51 of power 3, because the male has 3 chances, okay, and their probability is 51. So 0.51 of the power of their chances, okay. The female will have their probability is 0.49, okay, and they have n minus k is 3. The 3 chances, the male k is 3. I have total n equals 5, k equals 3, okay. N equals 5, k equals 3. So I have to choose 3 out of 5. So here for the male, their probability is 0.51, and I need 3 of them, so it will be power k, okay. And for the complementary, for the female, in case of non-success, it will be 0.49 of the power of n minus k, which is 2, which is this one. You can memorize the rule in case of it's difficult for you to digest it, but this is the way how it works, okay. So now I got the probability, but how many ways, okay, because there is not only one way. I have different ways of this combination, okay. So I can have the male first, the male second, the male third, so I have different combination. So that's why we came to the combination of choosing k out of n. Choosing k out of n, which will come to it. So here we knew the probability, it will be 0.51 over 3 times 0.49, which is this section. Okay, just remember it. We'll look at it after we go to the next page. Here in the next page, how many times of combination, okay, I can arrange this 5. So the first male, second female, third male, fourth female, or how many ways, okay? So this will be a combination problem. Choosing 3 out of 5, okay? Combination of 5 elements, choosing 3, okay? So it can be written this way or this way. It doesn't matter. So the formula will be here for the combination. 5 factorial, the first one factorial, divided 5 minus 3, which is 2 factorial, and the last one factorial in the denominator. So 5 factorial, I can expand it 5 times 4 times 3 factorial, and I leave this 2 factorial, 3 factorial. So 3 factorial will cancel with the 3 factorial. So 5 times 4 equal 20, and 2 factorial equal 2. 20 divided 2 equals 10. So here I have 10 ways to arrange these people, the male and the female, 10 ways, okay? And the probability of having 3 male is 0.51 over 3 times 0.49 over 2. So if I multiplied K, this one, the formula, so if I multiplied here, the combination, okay, C and K times P of power K, Q of N minus K, or if we multiply this one, or we split it into 2 steps, like the way he did it here. Here he split it into 2 steps, instead of using the law here and solving the problem. So instead of using this law, he split it into 2 ways. So he get it, the first part, he got the P of power K times K, Q of N minus K. This part, okay? Then in the next page, he did the combination and then he multiplied them, okay? So here it will be 10, the combination, and here the probability. So the answer will be 0.318, okay? So this is the probability of 3 males out of 5 persons. That formula appears to justify it. So here, the combination, here, and this is P of power K, K is 3, okay, N minus K, 5 minus 3 equals 2, or this way, it can be done this way. Both are the same. So here we'll be talking about the applicability. What are the applications of this binomial distribution? Binomial distribution, as you can see here, is applicable in situation where sampling is. I have one of these 2 scenarios. It should happen in order to say that this is binomial distribution. Okay, so I should have, if I have infinite population, infinite, very large population, infinite population, or I may have finite population, limited population, but with a replacement. So every time I have the same probability. If I have 5 patients this time, I take one of them. Next time also I have 5 options also. Okay, so with the replacement. So binomial distribution, it is applicable in the case of infinite population or finite population with a replacement. In practice, if the sample size is much smaller, this is the key point actually. If the sample is very small compared to the population, which is infinite population, or it is finite with the replacement, if the sample is much smaller than the population size, then the binomial model is appropriate. This could be a question in the exam, okay? That when we can use this binomial distribution, if the sample size is very small compared to the population size, okay? And even in some cases, even without replacement, they are using the binomial distribution. So we look at this example, which will clarify a little bit the issue. So in this example, it is a little bit tricky. I have 10% of the population is a blind color, or color blind, okay? 10% of the population is color blind. If random sample of 25, so this is the population, 10% of the population. And the sample, 25 of them, okay? So sample, the N will be 25, Okay, so n, and a sample of 25 is drawn. What is the probability that 5 or fewer? Okay, if you remember in the previous example, we have taken here 3. Choose 3. Only 3. But in this example, it is little tricky because say 5 or fewer. So it is not one problem. It's not one question. It is 5 questions. It could be 5. So the k here, k would be 5 or 4 or 3 or 2 or 1 or 0. Any one of these number, because he didn't say 3 or 2 or 5. He said 5 or fewer. So we have to go all the way down up to 0. So it could be 5, 4, 3, 2, 1, 0. So in this problem, I have to repeat the calculation, the probability calculation 5 times and then add them up, okay? Because if it is 0, it's okay, it will happen, plus the probability if it is 1, plus the probability if it is 2, plus the probability of 3, plus probability of 4, plus the probability of 5. So I have to get the 5 probability and calculate them. So we start with n. N here equals 25, and the p always for the required, the desired characteristic, the success factor, as they are calling the success criteria. Here, what he's looking for, he wants them to have blind color. It doesn't matter if it is a good criteria or bad criteria. Color blind is not a good criteria, but in our problem, this is the success. If it happened, this means that what is required in the question we have met. So this is the success criteria. They have color blind. Okay. If they don't have, this means that the failure of the success criteria, okay, or the success point which we have, okay. So 10% of the population is color blind. If the random sample of 25 n, so I have n 25, the success criteria which I needed is 0.1. This is the probability of it, okay. 10% of the population. So color blind, it is represented by 10% of the population. So the probability of it is 10%. Okay, so the people who are not color blind, their probability will be 1 minus 0.1, 0.9, because they are representing 90% of the population. So 10% has color blind and 90% does not have. So the probability will be in the same ratio. So probability will be 0.1, and the Q for the non-color blind will be 0.9. Then I write the formula. The formula which I have here, I just copied from the previous page. So the probability of x equals k, x equal 1 or 2, in the previous example it was 3 or 4 or 5 or whatever, equals c nk, okay, the combination of nk times p of power k times the q of n minus k, okay. So here if we assume for the first one, because I have 5 probability, it could be 1 k, I don't know what's k. K could be 1, could be 2, could be 3, 4 and 5, because he said 5 or fewer, okay. So here k could be any of these values, okay. All of them are k. So the first time I say that px equals 0. I put k with 0 first time. So my question will be combination of n equals 25 and k equals 0. So p of k, p of power k, which p of power 0 equals 1. Anything of power 0 equals 1. Q of power n minus k, 25 minus 0, okay, 25 minus 0. So it would be 25 minus 0. Then I write it. I just replace p by 0.1 and I replace q by 0.9 and I calculated on the calculator. You have the combination, which is shift the deviation sign or the division point on the calculator. You can get it directly, okay. No need to write n factorial divided n minus k factorial. So you can get it from the calculator directly. Just write 25, then the button of NCR, then 0. You will get it. And the same thing here also for the 1. If x equals 1, so it will be C 25 1, 10 of power 0.1 of power 1, okay, and 0.9 of power 25 minus 1, and so on for the rest. Then after we got all the probability of this one, you have to add up the sum of the probability, because he needs the probability of 5 or fewer. So this is fewer than 5, fewer than 5, fewer than 5, fewer. So all these are probability, and this one is the 5 itself. So all of them are the probability. So the probability of this happening plus the probability of this happening plus the probability of this happening. So all of them having this much probability as a sum. So the total probability here will be, as mentioned here, 0.9666, which is very close to 1. Very big probability. Okay? I hope this example is clear.